Hello again, party people. Now that we've talked about oxidation states, let's figure out how to determine them. Honestly, this is a rehash of determining the charge of an unknown ion in section N.2. We'll follow a series of sulfur-containing compounds as we work. Know that I use Roman numerals in this video because, again, I'm old. Standard numerals would be accepted for a quiz, assuming that the rest of the notation is entered correctly. For example, +2 versus 2 plus. Starting us off with a tiny trick. S8 is a polyatomic element. Now it looks goofy, but it's really just the same as any diatomic or monatomic element that you'll see more often. Anytime you see a single element listed with a subscript, kind of like we have here, consider that a polyatomic element. There's a handful of these, phosphorus and carbon being two others to look out for. The oxidation state of any element, even these diatomic and polyatomic ones, is going to be 0. Our next example, many will be able to do in their head, and good for you. But I'm going to work through this as you would a more complicated example, just for the sake of earning my paycheck. We are looking for the oxidation state of sulfur in this compound, which means we can consider it an unknown, which in turn means we can probably set something up algebraically to solve for said unknown. Sound familiar? We can do this by starting with our atom count. If we multiply the number of atoms by the oxidation state of that atom, we can get to the total charge on the species, which sounds a lot like algebra and would look something like this. Now we actually know that total charge though, because this is a compound. I know this is a compound because there's not a charge written anywhere near that H2S. So I can replace that total with 0 because compounds are neutral. We know that sulfur is the unknown because we're asked to solve for the sulfur. This means that we should know the oxidation state of everything else. And those oxidation states should be in their most commonly adopted ones. See the table on the content page. Hydrogen, the only other atom in this compound, commonly adopts a +1 oxidation state. I can substitute that for my hydrogen placeholder. Both substitutions mentioned gives me what I have here. All that's left is to solve for this unknown, which I've left as S. The value you obtain is the oxidation state of sulfur. Remember that oxidation states are reported sometimes as Roman numerals, so you'll likely see this as your notation depending on where you look. For this one, I'm going to roll the atom count and the algebraic equation step together. If this confuses you, go back in the video and reconcile the difference between these two steps from that H2S example that I just did. There's a single sulfur and 2 chlorine atoms in this neutral compound, so the algebraic expression should look like this. If sulfur is the unknown, then the chlorine atoms will each adopt their most common oxidation state, which is -1. I'll need to make that substitution in order to solve for sulfur's oxidation state. I'm going to do this next one 2 different ways, and you can pick the one that works best for you. Let's work on finding the oxidation state of sulfur as part of this whole compound first. That's going to give me 3 variables, which will eventually need to add a 0 because the compound is neutral. I can only solve for one unknown at a time though, so I must know the oxidation states of both the sodium and the oxygen, and those are probably going to be their most common oxidation states. Solving for sulfur is going to give me a value of +4, which I can rewrite if I want to as plus Roman numeral 4. Let's say maybe you're not a 3 variable kind of person. Then what? Well, you could recognize that the SO3 part of this salt is a common polyatomic ion, or the sulfite ion, and that ion carries a 2- charge overall. So instead of all 3 variables in the neutral compound being set to 0, you could just set the 2 variables in the ion equal to the charge of that ion, which is 2-. All 4 of the atoms in the polyatomic ion are going to share that overall 2- charge, and this would be how you would represent that fact mathematically. The remaining substitution and solving steps are going to be similar to what they were before, and the result is the exact same value. I did the last one 2 ways because sometimes you have no choice. Your species is a polyatomic ion, and you'll have to set your equation equal to something other than 0. The sulfate ion here is no exception to that. The setup looks very similar to the sulfite ion. The only difference is the number of oxygen atoms that are present. This difference will change the oxidation state on that central sulfur. Reviewing our whole table, we can see that the sulfur is capable of pulling electrons towards itself as it does in the H2S, or it can exist with quite the deficit in density as it does in the sulfate ion.